In this video, we're going to take a look at how to determine if a molecule is polar or nonpolar with the help of VSEPR theory. So, in general, when you are given a molecule and you want to figure out if it's polar or nonpolar, the first thing you need to do is draw its Lewis dot structure, and then you need to use VSEPR theory to figure out its shape. So, once you have its shape, you want to determine if the molecule is symmetrical or asymmetrical. For example, if we look over here, a symmetrical molecule is going to be a molecule where the dipoles actually cancel out, and therefore we're going to have a molecule that's nonpolar. In an asymmetrical molecule, the dipoles do not cancel out, and so you're going to have a polar molecule overall. And so the way to figure out if your molecule is symmetrical or asymmetrical is by asking the following questions. So first of all, we're going to ask, are there any polar bonds? That's our first question. If you say no, your next question is going to be, are there lone pairs around the central atom specifically? If you say no to that, so those two first questions you said no to, then your molecule is symmetrical and it's nonpolar. For example, CH4. If I were to draw its Lewis dot structure, let's do it over here. H, 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 H. You calculate all the electronegativity differences, they're all 0.4, so all nonpolar bonds. There's no polar bonds. There's also no lone pairs around the central atom. So this molecule here overall is symmetrical and therefore nonpolar. Now, let's say you went a different route. Let's say you said, are there polar bonds? And you said no. Okay, your next question is, are there lone pairs around the central atom? And you say yes this time. If you say yes, there are some exceptions, and we'll talk about those after, but for the most part, if you say yes to that, even though there's no polar bonds, your molecule will still be considered polar, and we'll see the exceptions later. But let's just look at an example of this right now. So pH3. If you calculate the electronegativity difference between all the pH bonds here, so let's say we just did that one for now. So let's go to our periodic table. P is 2.1 and hydrogen is 2.1. So we're almost pure covalent. I mean, these are rounded values, so it wouldn't be quite zero, but pretty close to zero. So our electronegativity difference for those bonds, delta En, is zero. So there's no polar bonds there, but notice that there are these lone pairs. And so these lone pairs cause the molecule to be asymmetrical. The lone pairs are negative, so overall you're going to have more of a negative charge towards the top of the molecule. So if you were drawing an overall dipole moment for the molecule, the arrow will be pointing up with a partial negative up there and a partial positive charge sort of closer towards the bottom half of the molecule. Keep in mind, if you were to draw this with vector shape, it would be more accurate because it would have a three-dimensional component to it. But this is considered polar overall. So this one here was non-polar. This is considered polar because even though there's no polar bonds, there's still a lone pair on that central atom, and so that makes it polar. So that's the scenario where you ask if it's polar bonds and you say no. Those are two possible scenarios. You could also ask the next question, are there polar bonds? So let's say you ask that question, are there polar bonds, and you say yes. It doesn't necessarily mean that your molecule is polar, so you have to ask a couple more questions. Are there lone pairs on the central atom? Well, if you say yes to both of those questions, then your molecule is polar because it's asymmetrical. And again, there's exceptions to that. But if we look at water, for example, water looks like this. The bonds are polar, there's lone pairs. So this is an overall polar molecule. The individual dipoles go this way, but the overall dipole moment goes towards the oxygen when you add them together. Partial negative, partial positive. It basically means that overall the electrons are more towards the half of the oxygen, more towards the oxygen half of the molecule as opposed to towards the hydrogen half of the molecule. Now, it is possible that you say there are polar bonds, and then your next question is, are there lone pairs around the central atom? And you say no. After that, ask yourselves, are the atoms the same? If you say yes, then your molecule is nonpolar. So if you look at CCl4 that we drew up here, all the atoms are the same. There are polar bonds, but there's no lone pairs. Because all the atoms are the same, all these dipole moments, these dipole vectors, I should say, dipole vectors from the CCl bonds, they're going to cancel out. So this is going to be a symmetrical shape, and overall this is going to be nonpolar. Nonpolar. Whereas if you had something like this where you said, are there polar bonds? You say yes. Are there lone pairs around the central atom? You say no. Are the atoms the same? You say no. Then it'd be polar because we're asymmetrical. You can look at CH3Cl, for example. So a lot of these are non-polar bonds, but you do have a polar bond here. And so the overall dipole moment is going towards that Cl side of the molecule. It doesn't cancel out because the atoms aren't the same. You're not pulling equally in all the different directions. Likewise, same thing for this one over here. The overall moment is towards the oxygen half of the molecule, because the atoms are not the same around the central atom. Not all the bonds have to be polar, but there should be some polar bonds. So the main idea is that if you don't have the same atoms around that central atom, and there's polar bonds there, then chances are they're not canceling out. To really cancel out, you need to have the same atoms around that central atom there to cancel out. And it all has to do with the shape. So if we look at our VSEPR shapes here, if you have a central atom with X and X, so those are just the same atoms, it means they're pulling with equal force in opposite directions, so they can cancel out and your molecule is nonpolar. If you have a central atom with X and Y, so different atoms, well, they're pulling in opposite directions, but this one's slightly larger, so the overall dipole will be more so in this direction over here, or the partial negative that way, and partial positive more towards the AX part of the molecule. So this would be polar. If you had a bent molecule, let's just erase that for a second, a bent molecule where you have lone pairs, for example, because of the shape being bent, like water, let's just say, the dipoles no longer cancel out, so it's polar. So it's all about that shape that's determining this. If you have trigonal planar, so three atoms around a central atom and they're all the same, they're all pulling with the same force in those directions, they're all going to cancel out, so nonpolar. If you have trigonal planar, but the atoms are not the same, for example, then they're not pulling with the same force. So you're going to have a bit of an overall net dipole more in this direction here. And so it would be polar. If you had tetrahedral, and they're all the same, peripheral atoms, then you're going to have the non-polar situation. If you have tetrahedral but they're not all the same atoms, then it's polar because, again, this is pulling in a slightly stronger direction, or with a slightly stronger force. Or it could be the other ones pulling with slightly stronger force. Doesn't really matter. And then here, for trigonal pyramidal, we have a lone pair on there. And so that's causing our molecule to be polar because it's asymmetrical. So this is all based off of the shape. That's what those questions in the steps are based off of. So if you understand that, then you'll be able to predict if a molecule is going to be polar or nonpolar based on your shape. I did say there were some exceptions with lone pairs. These are the two exceptions over here. These are exceptions you'll see mostly in grade 12. You'll see square planar molecules and linear molecules with lone pairs. And so what you can see is this is a square planar. You have two lone pairs in the central atom. This overall is still considered nonpolar because the CLs cancel out going in these directions here because they're going in opposite directions. And then the two lone pairs are symmetrical about the central atom there. And so they're going to cancel out going up and down. And it's kind of the same idea with this linear molecule over here. These ones cancel out here, and these lone pairs actually cancel each other out, going in those different directions as well. So those are the main exceptions that you can remember if you do come across them in a worksheet or in an extra practice problem you do, but they're the main exceptions. So let's do a couple examples together in this video. We'll do a few of them, and then we'll do another video where we do a few more examples as well. We're going to try to figure out if overall the molecule is considered polar or non-polar, and we'll have to indicate the bond dipoles where they're applicable. So we'll start off with the F2 molecule. The first step is we're going to draw the Lewis structure. Like that. And we're going to draw the VSEPR drawing and the VSEPR name. So this is just one with two atoms, and when there's two atoms, it's going to be linear. And we're going to figure out what the electronegativity difference is between the two atoms, and it's just two Fs. So that means the delta En is equal to 0, right? Because it's 4.0 minus 4.0. So in the case of a linear molecule like this, where it's just two atoms that are the same, there's no overall dipole because there's only non-polar bonds here. And there's no central atom with lone pairs. The molecule's left half is the same as the right half. So overall, we would say that this is a non-polar molecule. And it's really because there are no polar bonds, and it's a pure covalent molecule. So let's take a look at another example. Let's do the HF over here. Actually, let's change this to HBr. So we'll do the Lewis dot structure for HBr. Again, it's just two atoms connected by a bond there, so we know it's linear according to the VSEPR shape. And we're going to calculate the electronegativity difference of that one bond. So if we look at Br is 2.8 and H is 2.1. So delta En is equal to 2.8 minus 2.1, which is 0.7. So there is a polar bond. There's no central atom here, so we're really just looking at that one bond. So it's a polar molecule overall, that means. And it's really because there's a polar bond. And there's nothing else to cancel it out. And it goes in this direction here towards the more electronegative. So partial negative, partial positive. So let's try one where there's actually a central atom. So here we have CH4. Let's draw our Lewis dot structure as we saw in previous videos how to do. And let's ask ourselves some questions. So are there polar bonds? Well, if you calculate the delta En for all the bonds, you'll see they're all 0.4. So there's no polar bonds. Okay. So we're starting with one of these two steps here. Are there lone pairs? Well, no. So there's no polar bonds, there's no lone pairs. So that means overall our molecule is symmetrical. So it's non-polar. There's no polar bonds. There's no lone pairs. And we know the shape is tetrahedral. Because if you look down here, we have 4 electron regions. There's no lone pairs, so it's this shape over here. And so you can draw that, tetrahedral. And we don't need to put in any dipoles because there are none. So let's go ahead and do the one that goes towards the back. Now let's try CCl4. So let's draw its Lewis dot structure. Let's go ask some questions. Are there polar bonds? Well, if we calculate the delta En, we have C and Cl. So Cl is 3, C is 2.5. So we have 3.0 minus 2.5, which is 0.5. And that means there are polar bonds. Yes, there are polar bonds. So are there polar bonds? Yes. Are there lone pairs? No. Are the atoms the same? So if we say yes, they are, then this is symmetrical. The dipoles cancel out, and so it's non-polar. So it is I should add here. Therefore, symmetrical. Symmetrical. Here, there are polar bonds. There are polar bonds. There are no lone pairs. The peripheral atoms are the same. Therefore, symmetrical. So what that means is that this is non-polar. And you'll notice this is also tetrahedral, so it's very similar to the one we drew above there. And we don't really need to draw in any dipole moments because, well, they all cancel out. I could ask you to still show where they would be, but they all cancel out. So you can pause the video and try CF4 for yourself and see if you're on the right track with me. So if I do CF4 here, I'm going to draw out the Lewis structure first. We'll figure out if there's any polar bonds. So we're doing C minus F. So we have 2.5 and 4. So 4.0 minus 2.5 gives me 1.5. So we do have polar bonds. Now, if you look carefully, our question is, are there polar bonds? Yes. Are there lone pairs? No. Are the atoms the same? Yes. So that means it's symmetrical, therefore non-polar. So non-polar, same reasons as CCl4, and then very similar structure there for the VSEPR. And these are all tetrahedral. So you could draw in all the dipoles just to show that, you know, they are there, but they do cancel out. So there's no net. There's no net dipole because they end up canceling each other out. And this is a partial positive here, but they cancel out because it's a symmetrical molecule. It's all the same atoms. So in the next video that we do, we're going to finish the rest of the examples here, and then you should be able to attempt more homework problems. Before you watch the next video, you should try the next few examples on your own, and then use the next video to verify your work.